Okay, just to finish here, was next curve when we connect, that's also called a secant line. So change has to be linear. That's where linear functions in the previous section. In real life, we have curves, but we have rate of change, like how much it changes per unit time with approximating the change. Approximating the curve, what I wanted to say. It's a secant line, all right? Difference quotient doesn't really relate to us specifically. I'm not going to put you through that. So here you go. This is a typical problem that we'll see. You take a ball and it's shot straight up 64 feet per second. The equation that gives the height of the ball. So we want to know what's the height of the ball at a given point in time, assuming that it's thrown with a certain speed of 64 feet per second. All right. Well, we want to find the average velocity. Average velocity is the rate of change, the slope. Okay, the same term that we're talking about before, between 1 and 2. So we want to approximate the change from 1 to 2 with a line. All right, so that's what we're going to do. So put the curve in here for you so you can see. Just type it in here. Put x's instead of t's. You put x's. You can see at 1. So we're going to approximate that right here. All right, from 1 it's at 48 and 2 it's 64. So we're trying to find the average rate of change. So the average rate of change is going to be 64 minus 48. That changes 32 over 1. Okay, so we're going to approximate that. Y equals 32x plus, now times 0, it's going to be 0. Y equals 32x. So you can see that the red line approximates how much it changes. This right here, is the x-axis. There's the origin right there. So the red line approximates how the green line is changing from time 1 to time 2. Just want to show you that that's the secant line right there. All right. So average rate of change is 32. So on average, it's changing about 32 feet per second during that time. That's what that means. Did we miss something? F of 2. Oh, did I type in the wrong equation? Let's see here. Did I type in the wrong equation? Oh, no, we got it right. 64, so 1 is equal to 61 times 2. Oh, 64 minus 16t squared. So let's be careful when we're calculating the rate, okay? So we're going from 64 to 48. It's a change of 16. The average rate of change is 16, not 32. Okay, so 16. Between time 1 and 2, you're changing about 16 feet per second. Okay, and that is the average rate of change right there. Okay, so from 1 to there. There you go. And that's the answer that you see on here. So again, vertical change over horizontal, output over input. You can take a long time to do that algebraically. We're not going to do that. So the last problem here is telling us about enrollment of U.S. public schools expected from 1980 to 2024. There's a scatter plot. We have to make decisions about it. Does the line fit the points exactly? What's the average rate of change between these years? Write an equation of the line determined by this rate of change. So we take a look here and we say create a scatter plot. Does the line fit? So we could see that it's going up by 20 years. Is it going up by the same amount each time? It's going by 5,000 something. No, it's not a constant change. Not a constant change. Draw a scatter plot. So there's our scatter plot. So that we'd get if we type into the calculator. We don't need to do that because they did it right here for us. So we know how to do that. So we just type that in the calculator, into a table, just like that. 1980, this number, 2000, this number, 3000. So type that in your table. You can do that in Desmos if you like to. You just get your table and type that in and do that there. So we don't need to do that right now. We got it. Let's go down here. Keep saving. So we don't have to take the time to do that right now. We have it right down there for us. Then we'll know what's the first question. This is the analysis here. Is it a constant rate of change? No, it's not. I made a scatter plot. It's linear, but it's not exactly a line. That's what we need to know here. Find the average rate of change. So we go back to the table. We can pick any points we want. So I pick, like, for instance, we'll do that. Okay, so do y minus x. So we have 46,857 minus 41, so vertical coordinate, change in vertical coordinates, which is right there, okay, divided by the horizontal coordinates, which is 20, right? 2,000 minus 1980. So it looks like it should be about 260.3. To check the units on this, let's see the units. Is this millions? Thousands. Okay, so about 260,000 per year is our increase in the number of enrollment in U.S. public schools between what years did they say to do it between? 2024. Oh, my mistake. 2024. So if you go back to 2024 number, now it's 52,113. So we have to go back here, 52,113. I don't know why I just chose my own, 52,113. That's not good. And it's not 1980, it's 2024. So average rate of change should be 237,000. That's the change in population in U.S. schools during that time. Let's see if we got that. 237.7. Yep, 237.7. So we got the same answer here. So again, it's rate of change. I don't know why I picked my own numbers. Pay attention, read the problem carefully. Average rate of change between 1980 and 2024. So that's why that's our horizontal change. Our vertical is the y values that went with that from the table that I got right there. I got them from here and from here. All right, now let's go back on the last one. Write an equation of a line. Well, we know it's going to be y equals 2.37x, 0.23. Y equals 237.8x. We know that already. Now we have to figure out point slope form. So you could do this using point slope form. So we know it's going to be, you can use any point you want. So my advice, this is the case where you want point slope form. So y minus y1, you could pick any number from here you want. You can just choose the first one, y minus 41,651, okay, equals m, 237.8, we just found out, times x minus x1. So you have to use the x1, you have to use the number that goes with 41,651, which is 1980. And if you multiply that using the distributive property, this is what you would get. And then you simplify the x, you add 41,651 to both sides, add 41, and you get negative 429,193. So that's the case where an application of the point slope form that you'll need to write that out. If I can figure out the drawing tool on this, I will do that for next time. But we can do that in class if you want to see that step. All right. So basically, point slope. You're putting in the point there and putting in the slope here, and the point is 1980 over here for x1, and y1's over here. You do distributive property, and then you solve for y. Add 41,651, add it here, and this is the equation of the line. Talk more in class.